Okay, so when you have a non-zero difference in your potential energy, okay, so that delta E is not zero, right? Delta E is zero when there's no net magnetic field, right? Which basically means we haven't put an external magnetic field on. When it's not zero, the lower potential energy nucleus could absorb energy and flip. And when it does that, it effectively moves up to a higher potential energy until it flips back and comes back down. Okay? So when this is supposed to be an alpha. I didn't catch them all. So the alpha state nucleus, it absorbs a photon, right? Which is just a little packet of electromagnetic wave energy, right? It absorbs that photon. That causes its energy to go up. To express that, it flips over, right? So the magnetic field changes 180 degrees, okay? And it goes into the beta state, all right? And we call this process resonance, which is unfortunate because we have another a term for resonance, which has a completely different meaning, but this is a term that was used by people that studied spectroscopy. Okay, and so this is actually then, if you think about it, how we get the name for NMR, because NMR is talking about the nuclei, right, in a magnetic field absorbing energy, in other words, doing resonance, nuclear magnetic resonance. Okay, all right, now the important thing is that because the nuclei are very tiny, resonance is quantized. Okay, which means that those alpha and beta states, can P flips into an alpha? You mean a P orbital or phosphorus? You mean phosphorus? Oh, B, can B flip into A? Yes. I think that's, somebody asked me, correct me if I'm wrong, can B flip into A? Yes. And we're going to see that, okay, when we look at the modern NMR instrument, but I didn't get those notes typed in yet. But yes, when B, so let's say you had A, right? It was pointing this way. It flipped over to B, so its energy went from here up to there, okay? So here's the energy of alpha, here's the energy of beta, all right? Well, eventually, that beta nucleus could flip back over. And when it does, it's going to fall back down to the alpha potential energy. But that energy has to go somewhere. Well, where that energy goes is that nucleus lets go of a photon, and the photon comes back out of the sample. So we can put a photon in, right? So here I have a photon. Photon goes in, thing flips. Later on, it flips back. Photon comes back out. So that energy is conserved. Does that make sense? And so, in fact, what we're going to see is one of the ways that we do the NMR in our modern instruments, what we do is we blast it with a whole bunch of photons. Everything flips. And then what we do is we shut off the blasting. And then the things that are flipped over start to flip back, and they put out a radio signal, and we measure that radio signal. Okay. So, yeah. Okay. So, because this is a quantized phenomenon, what has to happen is we have an exact delta E. We have a photon, right? And photons have different amounts of energy. The only photon that will be absorbed is the one where the energy of the photon is exactly the same as the delta E. That's what quantization means. And that's extremely valuable and useful to us, because if it weren't for that, then just all energy would be absorbed, and we wouldn't be able to get any information, okay? And, okay, so how do we know the energy of a photon? Well, this is kind of a review thing. You should have talked about Planck's law in general chemistry a little bit. Planck's law is a physics thing, really, and in fact, you'll probably talk about it in physics also at some point. But basically, Planck's law says the energy of a photon is equal to h, which is Planck's constant, times nu, which looks like a little v, okay? But it's actually the Greek letter n, interestingly enough. But at any rate, E equals h nu. Nu is the frequency of the electromagnetic wave. In other words, how fast is that electromagnetic wave vibrating? Okay. And so since that's directly proportional, what you can see is there's a constant, right? But if a wave vibrates slowly, the energy is low. And when the wave vibrates fast, the frequency is higher, right? The energy is high. It's very intuitive if you think about it that way. So I did a little math derivation here. Again, this is kind of how physicists do stuff. They take some algebraic equation and then they do substitution and solve for something. And I can see that I screwed up and made that. Sorry, that's supposed to be an H. I guess I accidentally made it into a symbol font. So I'll have to fix that. But basically what you have is the frequency. If you solve Planck's law, right? So you just divide both sides by H, you get E over H is equal to V. And then we say, okay, E is equal to delta E. And we already had a formula for that. It was gamma times H over 2 pi times B net. So we substitute. We cancel out the H's. You get this. And again, the main point here is that this portion right here, this portion right there, that's a constant. So we have a similar kind of relationship. There's a direct proportionality between the larger the magnetic field, the higher the frequency that's absorbed. And so on a fundamental level, what we really measure in the NMR, what we do is we take a sample, we put it into a magnetic field, and then we just start putting in frequencies and see which ones are absorbed. And what we're really measuring is the potential energy difference, or by calculating back, the exact strength of the magnetic field that the nucleus feels. Okay? But it turns out we can then apply interpretation to get information from that. Now, I want to give you sort of a way to remember this because it's so important. It's going to underlie what we talk about next, okay? So what this equation tells is that as B net, right, B being the magnetic field, as the net magnetic field increases, the resonance frequency, in other words, the frequency that's absorbed, right? And remember, when it's absorbing, it's in resonance. So we call the exact frequency that a specific nucleus absorbs, we call it its resonance frequency. That, as B net increases, resonance frequency increases. And so to help you remember it, I made up sort of a silly little mnemonic, right? It's big B, big V, because the frequency, although it's new, it looks like a V, right? And it rhymes, right? So big B, big V. Okay? So just try to remember that. I'll be using that going forward. Now, the other thing I want you to know is a little bit about these electromagnetic waves that are going in there. It's not completely totally random. Once we have these equations, we can sort of calculate, if I put this magnetic field, what range of frequencies would be absorbed. And what we see is that the frequencies are in the range of between, the high tens, so like 60, 70, 80, 90. I've seen them as low as 40, okay? But then up to into the hundreds, so 100, 200, 300, 400. And the biggest, 30 years ago, when I was still in graduate school, we had an awesomely huge instrument. It was a 600. I've heard that they have 800s and they're working on gigahertz instruments, but they're in the hundreds of megahertz. And a hertz is basically just the unit of frequency. It's just, how many per second. Okay. and it's abbreviated M because it's mega is capital M, and then HZ, megahertz. And in fact, actually, I'll show you later, the instruments are built by picking a megahertz size for your external magnet, which is not really, megahertz is not the strength of magnetic fields, but they say this magnet with this B size would have this many megahertz. Okay, so they pick a megahertz size. And like I said, the bigger the megahertz, the bigger the magnet and the bigger the instrument. Okay. So it turns out that megahertz is basically the same frequency as radio waves. It's like when you go and turn on your radio, FM radio frequencies are megahertz. Okay. And when you are tuning the dial on your radio, you're just looking for different, broadcast frequencies of megahertz. So that turns out to be a really, really weak, low energy form of electromagnetic radiation. It's basically radio frequency waves, radio waves. It's very low energy. And so what that means is that these energy differences, these delta E's that we're measuring in the NMR are really very, very small. Okay. But if we're careful, we can still measure them and get information. Okay.